So in chapter 24, we examined a variety of electrophilic aromatic substitution reactions, and we focused primarily on substitution involving benzene, which has no substituents. Now, one of the things you're going to notice here is I have some pictures of aspirin, and what we're going to talk about in this chapter is electrophilic aromatic substitution on monosubstituted benzenes, as well as disubstituted benzenes. And so through these reactions, we can synthesize a molecule with two groups on it here, like aspirin, which is one of the syntheses that we do in our organic chemistry classes. Now, one of the things to be aware of is when you do an electrophilic aromatic substitution on a monosubstituted benzene, there are some additional issues. And one of those issues that kind of pops up is a regiochemistry issue. So in benzene itself, all 6 hydrogens are equivalent. So if you substitute one of them, it's going to lead to precisely the same product. If you have a monosubstituted benzene, all of a sudden now you have 3 chemically distinct hydrogens, right? You've got the ortho, which is the one right next to the substituent. You've got the meta, which is here. And then you have the para, which is here, which you can remember from when we learned how to name these. It's really helpful. I use OMP, O-M-P, to remember the order that these go in. Now, and so depending which one you get, ortho, meta, para, depends on which hydrogens replaced. And so what we're going to look at here in chapter 25, the substituent that's already on the benzene tends to direct the regiochemistry. And so some substituents are going to be designated as ortho, para directors, right? Because they're going to lead the product to product mixtures consisting of primarily ortho and para disubstituted products. And then other substituents are going to be designated as meta directors because they favor formation of meta substituted products. Now, notice that any of these 3 representations can be represented like this with a line coming out the middle. And so that's just a generic disubstituted benzene. That shows up in some papers, so I like that it's pointed out here. A second issue with monosubstituted benzenes is the effect the substituent has on the rate of the electrophilic substitution reaction. The rate of the electrophilic aromatic substitution reaction. I left out aromatic. Some substituents slow the reaction and therefore are called deactivating groups. So deactivating groups are going to slow the reaction. And then some substituents are going to be called activating groups. And they're going to speed up the reaction. And so the substituents that are attached to the aromatic ring can even alter the reaction mechanism involving the ring, making the ring more susceptible to reactions with nucleophiles rather than electrophiles. And we're going to look at 2 of those reactions in this chapter, and those are called nucleophilic aromatic substitution reactions. And then we are, at the end of this chapter, going to talk about how the characteristics of substituents on aromatic rings factor into organic synthesis. And so at the end, you should be able to design an efficient synthesis of targets with multiple substituents attached to aromatic rings. So let's look at phenol first. So phenol has 2 hydrogen atoms that are ortho to the hydroxy group here. Then it's got 2 hydrogen atoms that are meta and 1 hydrogen atom that is para. Each of those hydrogen atoms, if each of those hydrogen atoms were equally likely to be replaced by an electrophilic aromatic substitution, then the ortho disubstituted product would make up 40% of the products, right? 2 out of 5 equals 40%. Same thing with meta, 2 out of 5. And then because we just have one hydrogen here in the para position, that would be 1 out of 5, and it would be 20%. So when we did this reaction, we would expect 40, 40, 20. But what we actually see when this undergoes nitration is about 50-50 ortho-para. And so because of this, the hydroxyl group here because it favors those ortho-para products, it's called an ortho-para director. Now, we can also have, as I mentioned before, meta-directors. So when nitrobenzene undergoes nitration, M-nitrobenzene here, right, is the major product. And so because of this, the NO2 group here is referred to as a meta-director. So we can look at this table and see a summary of the ortho-para directing substituents, which are shown here, and then the meta-directing substituents, which are shown here. To help with this, they've got a third column, which is showing you the ortho plus the para percent yield, like the yields here. So this is, for example, 50-50, and that gives you 100. This is 19 plus 79, and that gives you 98. So just heads up there. In the next section, what we're going to look at is why do these substituents have the effects on the regiochemistry that they do. So, when we look at table 25.1, so you can just flip back. I can't, but you can, right? Substituents that are attached by an atom with at least one lone pair of electrons are ortho-para directors, okay? And so when we look back at that particular table, that would be things like, right, OH, right? It's got a lone pair of electrons, right? N, H, CH3, right? We've got a lone pair of electrons there. But then we also see that we've got substituents that are attached with no lone pair groups, orthoparas, and they are ortho-para directors if they are alkyl groups. And so that would be like an R group, right? So that CH3 group. Also want you to notice here, it's all your halogens have a bunch of lone pairs on them, right? So those are some examples there. And then I want you to notice that meta-directors, right, things are meta-directors if they have a point of attachment that is electronegative or is bonded to highly electronegative atoms. And so this is going to be things like your NO2, okay? This is going to be things like your carboxylic acids. This is going to be things like your cyanides. And so what we see here is, right, that these are bonded to these really highly electronegative oxygen, nitrogen atoms, okay? And so let's talk about why these characteristics dictate the different types of ortho-para or meta-directing behavior that we see. So to begin to answer this question, we need to remember that electrophilic aromatic substitution reactions generally happen under kinetic control. This means that the faster reaction wins. So this generally goes under kinetic control, okay? So the relative amounts of ortho, meta, and para disubstituted products produced in electrophilic aromatic substitution reactions are proportional to the rates at which they are produced. Right? And remember as well that the first step in the electrophilic aromatic substitution reaction is highly endothermic and is rate determining because we're generally forming that rhenium ion. And so we lose resonance and also end up with a positive charge, right? So what we're going to find is as that rhenium ion intermediate becomes more stable, the reaction rate increases. And so this leads us to a pretty useful generalization, which is the major product of electrophilic aromatic substitution is the one produced from the most stable rhenium ion intermediate. All right. And what we see here is that there's a difference in stability of the meta-rhenium ion and the ortho-rhenium ion. So in the nitration of phenol, for example, the distribution of products is 50% ortho and 50% para. So because a lot more of the ortho isomer than the meta isomer is produced, we know that in that case, the ortho intermediate, and I feel like I pointed at it incorrectly when I was talking about it a second ago. We know that the ortho-rhenium ion intermediate is lower in energy and more stable than the meta intermediate. So again, I feel like I either said it backwards a second ago or pointed backwards. So the ortho-rhenium ion intermediate is lower in energy, more stable, than the meta-ion intermediate. So the conclusions that we've drawn about the OH group, which is an ortho-para director, can be generalized to other ortho-para directors as well. And so what we can say in that case is when you have an ortho-para director attached to a benzene, the ortho-para rhenium ion intermediates are lower in energy, which means they're more stable, and are formed faster than the meta intermediate. Okay. Now the opposite is true of meta directors, which lead predominantly to the meta disubstituted product. When the meta director is attached to the benzene, the meta, so then the meta rhenium ion intermediate is lower in energy, which means it's more stable and is formed faster than the ortho and the para. So basically, when we get ortho-para, we're saying, look, in that case, the ortho-rhenium ion and the para-rhenium ion are lower in energy and they're more stable. But then it can also flip-flop. And basically what we can say is, look, sometimes the meta is more stable. So these two can flip-flop in their stability, not with this particular group on them necessarily, right? But it's based on, that stability is based on the group that these start with here. So let's dig around into that a little bit more, okay? So to this point, we've learned how to identify ortho, para, and meta directors empirically and how to use that information to determine the relative energies of the ortho, meta, and para iridium ion intermediates. However, we haven't really explained why the ortho, para, and meta directors influence the stability of the iridium ion intermediates in the ways that they do, which is going to be the focus of a lot of the rest of this screencast and into the next screencast. So, we've encountered two kinds of ortho-para directors: groups attached by an atom having at least one lone pair of electrons, or alkyl groups, okay? And so those are the two ones we see. When either of these groups is attached to a benzene, we know that the ortho and para iridium ion intermediates are lower in energy than the meta intermediates. And so when we look to see why this is true, let's look at the ortho and meta intermediates that are produced from the nitration of phenol. So this is the first step where phenol is nitrated. And if we were to form a meta, these would be the intermediates here. And when we form an ortho, these are the intermediates here. So when the nitration occurs at the ortho position, the iridium ion produces 4 resonance structures, 1, 2, 3, and 4. And when nitration occurs at the meta position, the iridium ion intermediate has just 3 resonance structures, here, here, here. And so the ortho iridium ion intermediate with its additional resonance structure is what makes it lower in energy and more stable than the meta intermediate. Then, right, the additional resonance structure for the ortho intermediate, which is highlighted right here, is due to the involvement of the lone pair of electrons on the OH. So look, the lone pair, right, because it comes down here, that's where we get our 4th structure. So the involvement of that lone pair is not possible for the meta intermediate because the meta intermediate has no resonance structure where this positive charge directly attaches to the carbon with the OH. So only because the ortho intermediate has a resonance structure where the carbocation is here at this carbon can we get the donation of these electrons as part of the resonance structure. So another thing that's really nice is that all the non-hydrogen atoms have an octet in this resonance structure, which is not true of any of the other resonance structures. And so that gives some additional stability that's extremely important. Now, similar reasoning allows us to rationalize why a para-iridium intermediate in the nitration of phenol is lower in energy than the meta, because we would see kind of the same resonance structures, okay? Now, let's look at alkyl groups. Like, why do alkyl groups do this? So maybe you're like, look, Dr. Pierce, I can buy why these guys do this. They got electrons, they can donate, and they can make this up. But what's the deal with alkyl groups? Well, remember, alkyl groups can also donate electron resonance, right, to stabilize carbocations. So that's why this resonance structure tends to be more stable, is because, again, the positive charge here is on the carbon of the ring that's next to the alkyl group, and this can donate electron density to stabilize this positive charge, okay? So even though ortho has 3 and meta has 3, even though we don't get a 4th one here, this charge stabilization is enough for it to favor the ortho and para intermediate. And para is going to have the same resonance structures that we see here. Okay? So, maybe your question is, okay, I can buy ortho para, but what about meta directors? Well, when a meta director is attached to a benzene, electrophilic aromatic substitution forms predominantly the meta substituted product here, right, which is shown here. Here's meta. And so that means that the meta-iridium ion has to be lower in energy than the ortho-para intermediate. And so why do we see this flip-flop? Well, again, we're going to look at the resonance structures. So each iridium ion has 3 resonance structures, right? The ortho intermediate has a resonance structure here where there's a positive charge on the ring adjacent to the NO2. Now, NO2 is an electron withdrawing group. There's a positive charge here and a positive charge here. And that nitrogen with a positive charge is going to withdraw electron density. This destabilizes the positive charge here. And that's enough to make those stabilities flip-flop, okay? And so none of these resonance structures have a positive charge on that carbon. And so that means that in this case, right, with any sort of meta director, you end up with the meta intermediate being the more stable, okay? And so that's why we're going to see different ortho, para, and meta directors and how the resonance structures influence that stability.